Welcome back to our afternoon session and our second plenary session. My name is Hisham Al-Adi and I came from the University of Salford, a very sunny Greater Manchester. First, I would like here to acknowledge the people of the Woi Wurrung and Boon Wurrung language groups of the Eastern Kulin Nation, on whose unceded lands we conduct the business of the RMIT University and CIB today. I would respectfully acknowledge their ancestors and elders, past and present. I would also acknowledge the traditional custodians and their ancestors of the lands and waters across Australia where we conduct our business today. This CIB World Congress is around building our future, building a world where our built environment improves quality of life, delivers greater social value, and reduces environmental impact. This can only be delivered by a world-leading, innovative, and sustainable businesses. I mentioned that I came from Greater Manchester, a city where such innovation is forged on the anvil of industry. From the Industrial Revolution to the streets of art lining the walls of the northern quarters, Manchester has been and has seen an abundance of creative, industrial, scientific, and political development throughout the years. Creativity continues to be at the heart of this Mancunian life force. Mark Farmer, another Salford link, in the excellent review a few years ago, stated that the way forward for the construction industry is the integration of skills, materials, and new technologies. I could not have found better than the National Graphene Institute in Manchester to represent that vision with its innovation in the construction sector, the use of highly skilled professionals, and of course, the production and research of its magical material, graphene. I think it was referred as God's material a few weeks ago in Dubai. Our next speaker, James Baker, is the CEO of Graphene at Manchester. James joined the University of Manchester after 25 years in industry, where most recently he was Vice President of Technology Collaboration Programs and Managing Director of the Advanced Technology Centers for BAE Systems in the United Kingdom. As the CEO of Graphene at Manchester, which includes the business responsibilities for the National Graphene Institute and the Graphene Engineering Innovation Center, he is leading on the creation of the graphene industry ecosystem in Manchester and developing the industrial partnership and collaboration to accelerate the commercialization opportunities for graphene and 2D materials. James is a chartered engineer and a fellow of the Institutional of Engineering and Technology, and also a fellow of Royal Society of Arts. Quite an interesting combination. Please join me in welcoming James Baker, who will deliver his speech online.
Thank you, Hisham, and good afternoon, everybody, from a fairly dark UK. Thank you for that introduction around Manchester, Islam. Delighted to be here this morning in UK. Apologies that I can't be there in person. It'd been great to be across in Australia, but a combination of reasons meant I'm delivering this speech from the UK today. So what I hope to do from that introduction is briefly to introduce graphene, but broadly two-dimensional materials and advanced materials. A little bit around what we are trying to achieve, not only in Manchester, but across the world in terms of pulling through these new materials for construction in support of sustainability. And I'll try and just give a couple of case studies where graphene is starting to play a real role in support of the built environment and around the drive towards sustainability. So my first slide. So what is graphene? In 2004, two scientists in Manchester, driven by curiosity, took some sticky tape and some graphite, and you can all try this later at home, in your office, in the kitchen. If you take that graphite and peel the sticky tape over and over many times, approximately 17 is said to be optimum. If you had an electron microscope, you might observe under that microscope that you had a single atomic flake or layer of carbon, what we call graphene. So graphene has length, it has breadth, but at one atomic layer thick, it is the thinnest possible material. You may say, so what? But when they started to measure this new material, it had unique and differential properties that led to the two scientists receiving the Nobel Prize for Physics in 2010. Next slide. So why was there so much excitement around this material? As a two-dimensional material, this material was stronger than steel as a single flake, more conductive than copper, flexible, transparent, could also act as a perfect membrane to allow some molecules to pass through, but to block others. So as a result of these properties, two-dimensional materials started to really excite not only the scientific world, but also started to get of interest for the industrial community. How do I use some of these two-dimensional properties in my aircraft, in my road, in my battery, in my structure? So next slide. So what we have in Manchester is, first of all, we have a National Graphene Institute. Just after the Nobel Prize in 2010, a lot of debate was really around how do we exploit the science around these two-dimensional materials. And the National Graphene Institute is a £61 million facility that really starts to bring together the multidisciplinary research around the physics, the material science, the chemistry, the engineering, but brings that together in a coherent body to really accelerate these new material developments. And today we have over 150 of these new two-dimensional materials. And if you look at the science, it's now about creating structures or layers of heterostructural materials that really start to build multifunctionality into your advanced material. The vision that Hislam said earlier really will be enabled by this whole family of 2D materials, and these layers were almost you could design into your material before you actually construct that as a new component or product or system. Today's presentation is probably going to focus more on our second facility, the Graphene Engineering Innovation Centre, that's really built around the transition of that science into products and applications. And whilst we've delivered over 150 new materials, the GEEK is more industrially focused and today has delivered well over 300 projects with over 150 industrial partners in this translational space of products into manufacturing, engineering and application development. Next slide. So what is the problem we're trying to address in Manchester? We often refer to it as the Manchester model. Anybody who's been involved in new material development can know it can take many tens of years from discovery through to those products in the marketplace. If we're going to really accelerate these new materials into construction, into aerospace, into automotive, into the energy markets, we need to do something much more rapid than traditionally it has taken. Carbon fibre, as an example, where many of you have flown an aircraft, was 25 years from discovery through to the first products in the marketplace. So graphene, since 2004 to today, is still a teenager. It is only 18 years young, so it's still quite early for a new material. But what I'll show later in this presentation is already we're starting to see those early products, those early applications in the marketplace. So really starting to condense the time to market for a new material into making a difference. So what we have in Manchester, next build, is still the academic work. Core to what we do is still the University of Manchester, the fundamental research. Next slide, next build. But we then have the National Graphene Institute, next build, which is really about extending that science from just the fundamental into those early concepts, those early ideas, those early designs. Key though, before going to industry, is sometimes what's referred to as the valley of death. So next build. So we have the Graphene Engineering Innovation Centre that bridges between academia and those industrial partners. But next build. But key to that is our partnership with industry. So really keen, as Hishlam talked earlier, is the ecosystem in Manchester, bringing together the supply chain, people who make graphene, bringing together the end users, the people who make products, the people who use those products. And what we're looking to create is all those businesses, not just in Manchester, but through partnership and collaboration around the world. So it's everything from large corporates to small businesses. In the last 10 years, we've achieved 44 spin-outs or startups at the University of Manchester associated with graphene businesses. Key to that ecosystem are those large companies, but also those small, new, disruptive startup types of businesses. Next slide. So just finally on the model, what's key if we're going to change is the whole innovation cycle. Keen to really engage with the construction industry around your key challenges, your problems. What are you trying to achieve? That could be sustainability. It could be stronger materials, more lightweight materials, more conductive materials. Where graphene starts to play a real interest is around what we often refer to as multifunctionality. Can I get a material that's both strong, but it's also firmly or electrically conductive? It's also got membrane properties that stops water absorption, as an example. So these multifunctional challenges or problems from your sector, our business model is very much around having a problem, making a component or a sample or a prototype, testing that. If that works, we then iterate that very quickly, or fail fast and learn and move on very quickly. So core to the model that we're working at Manchester is this rapid innovation cycle, but also a philosophy of building on that science and know-how, how we meet an industrial challenge and we iterate that very quickly into the market to reduce the overall time to market. Next slide. So where is graphene today? Graphene, as I said earlier, is 18 years young. How do you make graphene? Still, people can use sticky tape and graphite, as I said earlier. But today, people are now making graphene not by just the gram, but by the kilo and by the ton and even the tens of ton. In Australia, there are a number of graphene suppliers. Around the world now, there are suppliers who can provide what we often refer to as graphene platelets. So that's where you take graphite and you break it down into layers or few layers of graphene material. REACH registration, the European legislation for chemical production, has now been achieved by many of the suppliers. And now the price is coming down significantly, which combined with the fact that typically you need a very, very small amount. I'm going to give a case study shortly where we're adding as little as 0.01% graphene to make a real difference to the product performance. Uplifts of 30 to 50% can be achieved in some cases. So graphene supply is coming down. Also, price is coming down and volume going up, but also increasingly, people are also taking graphene from natural sources. So again, in support of sustainability, as an example, you can take methane from waste or from a byproduct of oil and gas, take that methane and break that down into both hydrogen, but also a graphitic material. So rather than having a waste like methane, we convert that into value-added hydrogen and graphene, which we can then add into some of our products and applications. The key message to the audience, though, is that graphene comes in many sizes, many forms, many qualities. There is no one graphene, to the extent that I often use the term graphenes with an S, in that there are many, many different types of graphene, and you really need to match the right graphene characteristics to a particular product or application. Next slide. So what are the applications that start to become of interest, particularly for this audience? So graphene is now moving very quickly as an additive in a number of areas. So generally, by adding graphene into something, you can start to improve the performance of that product. So typically what people are trying to do with graphene is, by adding a small amount of graphene, could I improve the performance? Or alternatively, by adding a small amount of graphene, could I use less of the material with the equivalent performance? So particularly driven by sustainability, if I can get the equivalent performance out of my product using less material, 30 to 50% less, that's lower over manufacturing cost, it's a lighter weight structure, but I don't compromise on performance. So again, we're seeing many examples where graphene is added into product. So things like protective equipment, if I can make lighter or stronger or more comfortable by dissipating the heat, then protective equipment is an area of interest. Thermoplastics, thermosets, carbon fiber, any material where you want to improve the properties, again, graphene is seen as a potential candidate. Ford in America actually put graphene into the foam that goes into the engine bay of their car. Not only do they make that component lighter, by having the better thermal management, they can now package that engine bay even tighter to get more efficiency, but it also reduces noise and vibration from the engine, and it's also flame retardant. There are over 5 million cars on the road from Ford, sports utility vehicles, now starting to incorporate graphene into their foam in their engine bay, as well as other companies looking to try and lightweight components. At the top end, carbon fiber, there is a car company in the UK called BAC Mono, who have taken 25% weight out of their components. Construction materials, I'll give some case studies in a moment, is of key interest. So concrete through to structures. Water treatment, I mentioned earlier about membranes. Can I allow water to pass through, but to block contamination is of great interest. Anti-corrosion coatings, some great examples on trial at the moment, getting some significant performance. We then go to things like electronics, some flexible displays, sensors, biosensors. Can I now print a sensor onto my clothing or my structure, onto my bridge, a strain sensor, a temperature sensor, again, an RFID tag, again, some real interest. And then we have things like shoes. You can buy a graphene shoe today. Why graphene? By putting graphene into the rubber, you can have a rubber that is both very grippy and very soft, but it's also very durable. So a company in the UK puts graphene in the shoes and now have a shoe that is now breaking records for running up hills because you get more sureness of grip, but it lasts up to 5 times longer. And then finally, batteries and energy storage have some very interesting work. Next slide. So just give a quick example of what the Geek is about. It's really about that scale up, that valley of death. How do I take an idea or a concept and rapidly take that from what's typically in a university made as a centimetre squared or a gram? We want to make something more at scale. So we're not a factory, but we make things by the kilogram, by the metre squared. And that scale up is quite key, both for the technology, but also for the business. Next slide. So just to give you one example of membranes, membranes has got huge potential. If we could take a membrane that we could take dirty, salty, contaminated seawater through a graphene membrane to create drinking water, that would create not only commercial value, but would create great change opportunity around the world. So some very interesting work around membranes. The National Graphene Institute is producing many papers, publications around the potential of graphene membranes, but the challenge is scale up. So what are we doing in the Geek? Next slide. We have a coating line that's from an industry where we're looking for continuous roll-to-roll production of that membrane technology in a scaled up application that industry can relate to. Water membranes are quite challenging, but already we have projects around salt separation for extracting salts from brine, through to can we just actually treat brown water to use that for irrigation or for washing. So we're not quite at the drinking water, but we are starting to produce membranes at some scale for test and evaluation. So next slide. So I want to just move the focus now really to around construction and sustainable construction with some opportunities and some case studies around how graphene can start to impact this sector. Next slide. So I mentioned some earlier, but clearly areas of interest are mortars and concrete. Concrete alone, I believe, contributes between 8 and 10% of the global carbon dioxide emissions. So if we can find a way of reducing cement or alternatives to cement, then clear interest. Our roads, asphalt and bitumen. I've touched on paints and coatings. Can we do anti-corrosion coatings? And in the UK, we're actually coating some crash barriers on the A1 motorway in the UK, where we've actually overcoated with a graphene paint that we're looking to try and either remove corrosion or overspraying where corrosion has started without that damage getting any worse. I mentioned around sensors and smart buildings, so building sensors into structures, whether it's your road, whether it's your high rise, and flame retardancy. Again, reducing the flame point of a material by dissipating the energy or the heat has got great interest. Next slide. So I just want to do a couple of case studies of where we are. I mentioned graphene is still very young, 18 years young. And if we do things traditionally, a new material, as I said earlier, can take many years, if not tens of years, to go from idea through prototyping, through testing, validation, and into the market. So on concrete, we're industry focused. So we've had a program of work with a small company in the UK called Nationwide Engineering. They're a small construction company based in the UK who visited the Geek just over 2 years ago with an idea around can they be more sustainable around their construction product and offer into the market. And working with Nationwide Engineering, we've developed a product that normally is called concretine. Everything with graphene tends to have an E. Other people in the market have cementine, other products. So there's a number of graphene enhanced concretes being worked on, including in Australia, a company called First Graphene. I know are working with Australian universities. So a number of companies have seen this opportunity of by adding graphene to concrete, can we use less concrete for the equivalent performance? So what we've been able to do in the UK, working with Nationwide Engineering with concretine, by adding as little as 0.01% graphene into the concrete. The other significant thing we've done with concretine, and I know others are doing similar, is this is something that can't take place in a laboratory. It has to take place in batching plant, in cement mixers, with existing skills, existing processes, existing equipment. So concretine is an additive that is added like any other additive at the batching plant through the standard material handling processes, but as little as 0.01% graphene into the cement enables you to design a slab for certain applications up to 30% thinner than a traditional slab for that performance. So this is achieved through a combination of the increased strength through to the properties of graphene and the reaction of the graphene when you add that into the cement. Gives you a different density, a different type of cement that enables you to use up to 30% less material, but also in some cases enables you not to use metal reinforcement or rebar. So in the UK, our process has been around that testing, that development, but we've also undertaken what we call living laboratories or living labs, where we've poured over 800 tons of this concretine into real projects, real applications. On the top, we have a lay-by outside our building in Manchester. So it's a fairly small 3-bay lay-by, but it's got lorries parked on it, it's got traffic, but it's not a safety or mission critical slab of concrete on a motorway. So if it fails, and it fails, we need to learn, but we're getting real data from that, and it's now been laid for over 6 months. On the bottom is actually a 54 metre by 40 metre slab of concrete. Again, it's a refurbished building in Manchester that is currently being used as a bar and as a roller skating ring, and it's suspended over a steel frame, but 54 metres by 14 metres. So it's a fairly substantial slab of concrete, no metal reinforcement in that particular slab of concrete. So what we're really doing is this living lab. Through doing these real pours, we found out additional information. For example, as well as the improved performance using less material, we've also found that we achieved the cure cycle or the cure time within 12 to 24 hours that typically can take up to 28 days. So again, that's quite transformational. And as an example, the slab of concrete on the bottom, when it started the pour at 10 AM in the morning, at 2 PM in the afternoon, they were doing the front end of the hall, and the actually polishing machines were actually on the back end of the slab on the afternoon of the actual pour taking place. So again, I believe that's quite unprecedented in terms of being able to do that in such a short period of time. And again, need to talk to the team, but they have a reduction in cracks, no expansion joints. So a lot of interest around the potential of graphene enhanced cements, and some very interesting trials taking place around the world in terms of reducing the amount of cement or concrete. Because if we can use 30% less, that would be a global reduction in CO2 of around 2–3%. So of great interest if we can achieve that. And I mentioned earlier, we've got other partners who are also looking at using cement and water-free construction. One of our partners is using chopped up plastic, reusing that plastic as a polymer to combine with aggregate for a cement-free concrete or structure. Again, some quite interesting initial results, but quite an early stage of development. The next case study I just briefly wanted to touch on was around roads. I'm sure in Australia, like the UK, we have a problem with our roads, in that the roads in the UK tend to have potholes. So if we could get a road that is both strong and durable, but it is also flexible during heat and during ice, so we get less cracking, that then gets delamination, that gets potholes, then again there's some real interest. And in the UK, working with the National Highways Organisation. So this is a good example of our partnership. National Highways are a partner of the GEEK. They're an end user, they don't make things, but they specify product. They bring their supply chain to the GEEK, we work with them, and we develop new forms of graphene, composite, bitumen, spray paints for the crash barriers. white lines that are more durable. So again, a good example of bringing together that ecosystem of suppliers to develop new products, new applications that will benefit the road network. So what we did with National Highways is we did a section of, as well as the testing, we did a section of a live road trial. So it's a section of the A1 main road in the north of the UK. And it's several miles of total recycled aggregate, but on one section of that, we've done a graphene enhanced section. So we can compare that in performance with the baseline solution. And again, initial results look promising, but we're now doing those tests and the evaluation as we talk. So again, it's a good example of collaboration, bringing together the best of industry with in academia, but also starting to create that both existing and new supply chain in support of a sector like construction. So I have many other case studies I could talk about, but they're probably the most relevant for construction. But as I've touched on in the presentation, it's everything from sensors to energy storage. We have partners in the UK who are now looking at new forms of modular construction using recycled materials. One of the key factors we're seeing with graphene is that often when you recycle a material, take rubber as an example, if you take a chopped tire rubber and you try and recycle that, you have a very poor performing rubber. But by the addition of a very small amount of graphene, you can upcycle and you get a performing rubber that has got better performance. So again, a small company in the UK takes chopped tires, a small amount of graphene into the rubber and produces flooring or mats or rubber components. And again, we've done some testing. Typically those components are up to 1/3 thinner, but up to 5 times stronger. And there's some great videos online if people have got the time. If you YouTube Graphene Manchester, you'll see some of these videos online. So final slide. So that's really the end of my presentation. As a vision in terms of what we're trying to achieve, and Hislam, thank you for that introduction. Manchester has some famous from Cottonopolis in our past through to what we hope in the future will increasingly become what we know as Graphene City. Thank you for listening. Happy to take any questions, and I hope that was some informative information around graphene, but also in terms of what we're trying to achieve in support of sectors like construction. Thank you.
Thank you very much, James. It is very difficult to cover such topic in 45 minutes. I only have to talk to James for 10 minutes and came out with 100 ideas very quickly for research. But we will have time now to get you to ask questions. So I would like to ask Don Ward to join me on the podium here, start some discussion with James about his presentation. And I'm hoping that we will be able to get some questions from online as well. If you can pass them to us, we'll be able to feed them back to James.
Hi, James. Don Ward here. Good to talk to you again.
Hi, Don.
We spoke back in well, December actually, just before Christmas, looking forward to this conference. And what's it been like in the last 6 months in terms of developments in the construction examples you're giving? How quickly is this moving?
So thanks, Don. It's a really good question. So we can never move fast enough is probably the answer. Yeah, we've poured 800 tons of concrete. That sounds a lot, but for me, it's the tip of the tip of the tip of the tip of the iceberg in terms of construction. They're still relatively simple pours. One thing we have done, if I can use the term, is we're on the road now. I can't say too much, but 2 weeks ago we did a concrete pour in an overseas territory, and that was at 45 degrees heat and very high humidity. So again, it was really just to try and understand whether this material is transferable. We're also using different materials like water, desalinated water. I've probably given quite a few clues there. So desalinated water, 45 degrees, high humidity, and the initial results look very encouraging. If they're positive, we're going to do a fairly significant concrete pour overseas, hopefully within the next 2 months. So we continue to do this test and evaluation. They are still very what I call safe pours. It is roads, it is parks, it's not bridges, it's not high-rise construction. So it's all part of getting more data, more confidence, more understanding of the performance of the material. So I think it's moving quickly in terms of interest. The data that I talked around earlier, clearly has great value to the construction sector. But the challenge we're facing is this is still quite young as a material. We change the supply chain slightly, or we change some of the variables, and we get slightly different results, and we don't fully understand that. So again, it's a good example of what I call the Manchester model. We want to complement that engineering with sound scientific understanding and data. So it is moving, it's moving at pace, but probably not at pace that the sector would really want us to go, because we're still trying to understand the technology, the science, as well as the engineering. But if this pour takes place in this overseas territory, a key part of doing that is to really then look at the certification, the approvals, the regulation, and we have that customer on board very strongly who wants to achieve that. So I'm hoping in the next few months we'll have more news, and hopefully we'll be able to talk even more about these test pours and some of the data we get from them.
Let's check first if there is any question from our audience today. Can carry on.
Bear with us, James, while we get a microphone to one of our
questioners
questioners in the audience.
Yeah, until we get ready for the next question. We talked a lot about graphene with this multidimensional effects. And for each of them, we probably can think of very large number of applications, whether it is fire resistance, whether it is waterproofing, and also, most importantly, its flexibility as well. So where do you find the most interesting problem that need to be resolved if we apply it in construction?
I think you've summed it up very well. I think the most interesting property is, can we achieve more than one of those features using the graphene? So the challenge, without making it too complex, is how do you add the graphene? Is it as a coating? Is it within the structure? Is it an additional layer within the overall structure? So I think the challenge is achieving the performance that you need. So for example, if I add too much graphene to the material, I can make it stronger, but it then becomes very brittle and unworkable. So it ends up being fragile. So for me, to answer your question, is I think the most interesting bit is optimizing the right graphene for that material for the application. And that's without overselling the geek. You can all try this at home. You all go home, try adding some graphene to some cement. It might work, but getting it to work repeatably with the right dispersion, with the right performance in a engineered solution is probably where the biggest challenge still lies. So concrete is an example. Some very interesting work I was aware of a number of years ago around carbon nanotubes. to get performance of high performing concrete, but to get the dispersion, to get the performance on a regular basis, repeatable basis, was really challenging. So multifunctionality is the answer to your question, but getting that performance repeatably is the real challenge.
Yeah, it is interesting as well. The other way around is we don't know what we don't know, so we don't want to start with the problem that it doesn't exist yet. So that's another question for us, really. But let us move to the next question here.
Yes, thank you. I'm Brian Kleiner, Virginia Tech, from the United States. And it seems to me that your experiment, if it will, exhibits best practices in terms of intellectual properties, the commercialization process. Could you describe a little bit more the process that has led to obviously successful relationships between the university and industry? What are those best practices?
So certainly, try. So like many universities, the University of Manchester, you know, when it's fundamental research, then the intellectual property model is quite complex in many universities. I'm sure you've worked in different universities. Every university is different, but typically universities either like to own the intellectual property for fundamental research. But for me, that's fraught with challenges in that universities aren't always the best places to exploit that. In our GEEK facility in particular, because we're working on high TRL activity, we allow industry to own any foreground IP that is generated in the GEEK. So using the concretine example, the foreground IP and its patent pending is owned by the industrial partner, Nationwide Engineering. For me, that's the best practice because industry are better placed to exploit that. Universities, when they own the IP, are always the most agile or the most positioned to exploit or to protect or to pursue any infringement of that IP. So the business model of the GEEK, for me, good practice is industry owns the IP, but we've also developed a framework contract, a bit like joining the gymnasium. It's a standard framework contract, and we have two tiers, a tier 1 and a tier 2 that industry sign up to. For me, the vision of that is a bit like Amazon in universities. If anyone's had experience of going to universities, my experience from industry is it could take 6 to 9 months to negotiate a contract with a university. Just the time, the complexity, quite slow. For the GEEK, we have a framework contract you sign up to, whether you're Airbus, Boeing, Lockheed Martin, or an SME, it's the same framework contract you sign up to. And it's really based on agility that you can sign, have a conversation in the morning, sign in the afternoon. You can be in the GEEK the next day doing experimentation under that framework contract. So again, happy to share outside of that if that's of interest, happy to share my details, but framework contracts, standard clauses, but it's really driven around agility rather than trying to own IP and to negotiate that when we don't really know the value or the understanding of that work. Hopefully that helps.
So I don't know if you could see, but you were certainly getting some nods in the room there, James, from that offer from Brian. President-elect of CIB, Mark Hastak.
Thanks, Don. That was a very interesting presentation. I was wondering if you had also used graphene for fiber-reinforced polymer applications, and if so, were there any issues related to pultrusion that you might have come across? Thoughts, please.
So it's an area of growing interest. So for me, I touched on it a little bit earlier. There's a lot of questions around how you add the graphene. Do you add graphene to a resin, or do you actually coat the fiber? Not quite your question. There's a lot of interest around carbon fiber. So for aerospace, for pressure vessels, for space, we have a partner in the Geek who's looking at something called space habitat. So this is a carbon fiber where early days people putting graphene into the resin and then mixing that resin with carbon fiber, but you weren't getting a very uniform weave structure. So people are now looking at coating the fiber before actually doing the robotic weave of the carbon fiber. So this is around pressure vessels for hydrogen storage, through to structures, through to ultimately space habitat, low Earth orbital satellites. On the protrusion, we've actually got some work going on at the moment around that space. People are looking at different, I mentioned earlier, recycled type materials. Again, I haven't got the full data on that, I'm afraid, but yeah, there's some interesting work looking in that space at the moment. The challenge is getting the uniformity of the fibre and the overall mix and getting some performance from that.
Next question on Brian Kleiner's table.
Thanks. Nick, RMIT. There are some safety concerns around graphene, as I understand. My understanding is not great, but how's that woven into the research to ensure we don't get ahead of ourselves, because construction does have form in that space around materials and getting excited about their properties and discovering later that potentially there are problems.
Yes, so it's a good question. So graphene is a form of carbon. I used this term earlier, graphenes with an S, in that there are many different types of graphene material. There were certainly some concerns around carbon nanotubes as an example going in the past. I mentioned about nanotubes in concrete, but one of the challenges with nanotubes is they tend to form clusters or clumps, and there were certainly some concerns around toxicology of nanotubes, some papers that caused some concerns. Graphene is different to nanotubes. It's not a tube. It tends to be platelets or sheets of graphene. There's a lot of toxicology studies taking place, and one of the key areas of interest for graphene is around biomedical applications. Trials are taking place at the moment, actually in the UK and in Spain, of actually putting a graphene anode into the brain that can re-stimulate the synapses after a stroke. So live clinical, live trials, currently non-human animal trials looking around, everything from graphene membranes in the brain through to drug delivery, through to skin tattoos are being studied. So a lot of work around toxicology taking place. I can point you towards the European graphene flagship. So there is a €1 billion program coming towards the end now that's got a whole package of work looking at toxicology. The most recent study that was published looked around graphene in a polymer that was then end of life, was shredded and looked at disposal issues. So there's a growing evidence of data around toxicology, around product safety that's being built up. I'll point to the fact that it is carbon, but then I'll also say, there's a lot of unknowns that we don't know yet because it's relatively a new material. I say that with sort of caution, is that we don't say it's a new material. Graphene has always been there. We just didn't understand that it could exist as a single layer of carbon. So it has these unique properties as a 2D material compared to a 3D. If you leave it naturally, it will just stack up itself as graphite. And again, we know the performance of graphite. One thing we are doing, though, to also answer your concern, is in the UK, we are running a workshop this year with Health and Safety England, the national regulatory body. Clearly, occupational health in terms of handling a powder. The Geek is full of fume hoods, extraction. We don't handle graphene in an open environment. We handle it in in a controlled environment. On the concretine example, to get round those issues, we didn't give a packet of powder to the batching plant. We actually dispersed the graphene into a water-based liquid, and that's what we added at the batching plant. So again, to address it in the actual manufacturing process, rather than handling powders, we actually address that by making a liquid solution that is added at the batching plant. So no powders, no issues associated with handling a fine dust or a fine powder. So yeah, growing body of evidence. I'd point you towards the graphene flagship if you particularly wanted to look at some of that evidence. And we're running a series of workshops and activities in the UK, but I know also in the US and overseas there are similar types of bodies and activities. So in US it's people like NIST and MPL in the UK, some of the measurement labs looking at not toxicology, but some of those issues around standards, measurement, verification that are taking place.
Yeah, we can have another 5 minutes if there is any question, any other question.
Yeah, so there isn't a Q&A session after the tea break, so this is your opportunity to talk to James Baker in Manchester.
Yeah, I thought Nick's question is quite interesting because in the world that we have a lot of information coming from everywhere about any new materials, and particularly in graphene at the moment. I mean, when I talk to people about graphene, and with an S, as James taught me, that it is, a lot of people talk about carbon fibers, carbon sheeting, and so on. So there is a mix of knowledge out there. And I just wonder, following Nick's question, how do you see the, how can we protect the idea of what graphenes are and how to stop other ideas, which is less quality, how to control quality of that coming into the supply chain in the construction industry?
Yeah, I touched briefly the last answer around standards. What is graphene? So why do I use graphene with an S? So graphene is now defined up to 10 layers of carbon. Beyond 10 layers, the properties start to change more towards nanoplatelets or graphite. So there is a big discussion debate around standards. I mentioned National Physical Laboratory in the UK, understanding the verification, the validation. So we partner with MPL. We're doing a lot of work around trying to build not just what graphene is, but standards for performance. Again, if people are really interested, there's some work out of an organization in the US, has a grand title called the Graphene Council. So it's a US-based organization. They've launched a new graphene performance validation framework, of which a number of the graphene producers are voluntary starting to adopt that. This week in the UK, there's a meeting of about 120 of the principal graphene manufacturers from around the world. Principal, careful my language, there's probably very few Chinese at that meeting, but certainly the UK, European, Australian, US graphene producers are likely to be there. And there's a workshop on a meeting on Tuesday of this week, followed by advanced materials show taking place. So there's a number of the graphene suppliers are starting to do some of that regulation, Islam, but it's a challenge. What we don't know is what people are doing in their shed or in their back room, or and calling it graphene. One of the key things I think is happening now, which I think is a key state of development. 5 years ago, there were a lot of companies who were talking about, for example, having a graphene paint. I've got a new graphene paint or a new graphene rubber or a new graphene widget. And they were using the graphene as a bit of marketing, as a bit of selling, you know, trying to up the price or sell their product based on the graphene name. Increasingly, I'm seeing now products on the marketplace that's there and they don't even talk about the graphene. The graphene's there because of performance, not because of the graphene hype. And I think that's a key development, that people are now selling product based on performance, not on the graphene wonder material that you touched on earlier. And I think the more we see that, the more evidence you'll find that people are using graphene, not for the marketing, but for the performance. And I think that's a key change that you're starting to see in the market.
Okay, I think we came to the end of this session. I think there is a lot of questions about the material and the development of the material and the future of this material. But let me here thanks James for joining us today. It's a shame that we are not with us in not very sunny Melbourne. I guess it's sunnier at your end. But thank you very much, and please join me in thanking James.
James, thank you for joining us at, what is it there, 5 a.m. or something when you came online? Yeah, much appreciated for the early start. And yeah, really enjoyed hearing about the progress you've made, and I look forward to catching up in person before too long. Thanks.
Okay. Okay.
Hisham's just reminding me, in the programme that's scheduled as a Q&A after the coffee break, there isn't a further Q&A. In effect, we just did that. It's tea break now. Yeah, great. Enjoy the tea or coffee maybe.